So today we start our new unit. We go from kinematics to dynamics. Kinematics, as you know, the last unit that we covered was the study of motion without regard to what causes the motion. We were studying how fast something was moving, how far something went, the acceleration of something, but we didn't pay any attention to what caused the acceleration or what caused the motion in the first place. This unit we're studying dynamics. Dynamics is a study of motion with regard to what causes the motion. In other words, dynamics is a study of forces. So this unit is going to be all about forces. Now, because it's still the study of motion, the stuff that we looked at in our last unit in kinematics is still perfectly valid. We'll still use those group A equations and those group B equations and so on. But now we're going to introduce that next component to it, okay? Not just the acceleration is equal to delta V over delta T, but rather the forces that cause that acceleration that's equal to delta V over delta T. So there's a little bit more to this unit. Less equations, but more overall because we use less new equations, I should say, but more overall because we're using some new stuff that we learned in this unit in addition to the stuff that we already learned in the last unit. So the study of forces, that's what we're going to spend the next few weeks on. What is a force? I know you guys learned this in grade 6, if not before. It's a 3-word definition. A force is a blank or blank. A push or a pull. Simple as that. The way you defined it in grade 6 when you did your unit on flight is just as good of a definition as I can give you in physics 20. It's a push or a pull. There's nothing more fancy about it, nothing more complicated about it. If you push something, you're applying a force. If you pull something, you're applying a force. Now, we are going to talk a little bit more detail about what that force does. Okay, in science 6, you talked about force lifting a plane up into the air. You talked about the drag force, right? You talked about the thrust force. Right? Do you guys remember that? But I'm going to tell you about a little bit more than just the motion that it causes. A force can cause motion. In other words, it can cause an acceleration. Now, acceleration, by the way, isn't just what we typically think of acceleration. Acceleration, we think of it as speeding up an object. So it can cause an object to speed up, but it can also cause an object to slow down. It can also cause an object to start if it's at rest. That's the same thing as speed up, really, right? It can cause an object to stop. Here's the one that people will miss all the time. Speed up, slow down, start, stop, change direction. When you're traveling down the highway at 100 kilometers per hour, and you go around a turn, you accelerate even if your speed remains 100 kilometers per hour. Acceleration is not change in speed over change in time. Acceleration is change in velocity over change in time. And if your direction changes, your velocity is changing. So even though you may not change speed, you can still change velocity by changing your direction. So what does a force do? It causes an acceleration. And that can be causing an object to start or stop or speed up or slow down or change direction. What do you think the other thing that a force can do is? It's not really related to acceleration. When I push on this wall right now, what am I doing to this wall? I'm accelerating the wall. Am I causing the wall to speed up or slow down or change direction? No. When a basketball hits the ground, okay, it does change direction, it does slow down, but it also does what? If I go to, you know, those big blue exercise balls, right, that you go to sit on sometimes, whatever. I'm not sure what you're actually supposed to do with those exercise balls. You know what I'm talking about, though, right? Those big ones that kind of sit on the ground and you exercise on, whatever you do with them. Okay, you sit on that exercise ball. Okay, you're applying a force on that exercise ball. You're pushing on that exercise ball. Are you causing it to speed up or slow down or change direction? No. What are you doing to it? What are you doing to that ball? What are we doing to the basketball? What are we doing to the wall as I push on this wall? I'm changing the shape of it. I'm deforming the object. So sometimes you can accelerate the object and deform it as you do with the basketball. Sometimes you just accelerate it and not deform it. Sometimes you just deform it, as in the case of that exercise ball when I sat on it. When I say deform it, I mean change the shape. So a force has to do one of those two things, or both of those two things. Even when I push on this desk right now, am I accelerating the desk? No. Am I deforming the desk? A little bit, a tiny little bit. Not a measurable amount probably, but I am deforming it a little bit. Does that make sense? You can see it a lot better when you sit on the exercise ball than you can when you push on a desk, but it's the same effect, just to a lesser degree. What's a net force? What does net mean? Who has a job here? Who has a part-time job? Not very many of you. Good. That's good. But not very many of you have a part-time job. If you do have a part-time job, you get a pay stub, right? You get a paycheck and you get a pay stub. And the pay stub lists all kinds of different things. It lists how many hours you worked, what your rate is per hour. It lists if there was any money taken off for employment insurance or any money taken off for Canada pension or for income tax. For you guys with part-time jobs, you probably don't get very much taken off because you got to make quite a bit in order to have a great deal of stuff taken off. Your gross pay is what you make before anything is taken off. They multiply the number of hours by the amount per hour. That gives you your gross pay. Your net pay is the total pay that you receive after you add together everything, including the negatives, right? We add together the amount of money that we make for the amount of hours that we work. We add together as a negative value the amount that was taken off for income tax and for Canada pension and so on. We add to that the amount that you get for sick leave if you happen to have some kind of sick leave provision. Okay, we add all of our monies together, everything that was added to my check, everything that was taken off my check, we get the net pay. The gross pay is what I start with. The net pay is the total after I've done everything to it. The net force is the total force. The total force acting on an object. Now, sometimes that total force is balanced. Sometimes if I apply a force to the right and I apply a force to the left and they're equal and opposite, then those forces are balanced. Many times it's unbalanced. If the net force is not zero, then it's an unbalanced force. So what's the total force? What's the unbalanced force acting on an object? What's the net force acting on an object? Those of you who have part-time jobs, when you get that pay stub, do they take a lot off you guys? Probably not, eh? For income tax and stuff. $100 off. Okay. It's amazing once you become an adult and you make like adult money, which teachers don't make a fortune, but we make more than you do at McDonald's, right? It's amazing what they start taking off. Like literally, you'll lose sometimes upwards of almost half sometimes. Almost half of the money that you make disappears, gone before you ever see it. So I don't know. I think they should change the terminology around. They say your gross pay is what you start with and your net pay is what you end with. Okay. After they take off, a few $1,000s at the end of the month, I think that should be called the gross pay. I think it should be called the gross pay after you see what you have left, because that's the gross part of it, is after they take off a couple $1,000s for whatever. The more they make, the more you make, the more they take. That's right. That's right. So the net force is the total. It's after we add everything together, whether you're talking about pay, whether you're talking about forces, whatever. Net means total. Sum. Okay, add everything together. Here's another term. You guys still watch Bill Nye videos in junior high school? Still? Bill Nye's old, eh? The beginning of the Bill Nye episodes, they always say inertia is a property of matter. Remember that? What's inertia mean? Don't tell me it's a property of matter. It is, you're right, but that's not a definition. Inertia is the tendency of an object to resist a change in motion. I'll explain that in a second. A tendency to resist a change in motion. If a car is traveling down the road at 100 kilometers per hour, it has quite a bit of mass, and it has a tendency to resist a change in motion. It doesn't want to speed up. It doesn't want to slow down. In order to cause it to speed up or slow down, you need to apply an unbalanced force. You need to apply a net force. But it resists that. It resists its motion changing. Similarly, that same car that's sitting at rest in the parking lot will resist a change in motion. It doesn't even want to start. So a car that's moving doesn't want to move faster. It doesn't want to stop. A car that's not moving doesn't want to start. They both have inertia. They both have a tendency to resist a change in motion. They want to keep doing what they're doing. If they're moving, they want to keep moving. If they're at rest, they want to stay at rest. A tendency to resist a change in motion. What do you think it is that affects inertia? What property is it that inertia depends on? It's not speed. Okay, a lot of people think inertia is related to speed. Right? The tendency to resist a change in motion. It's not related to speed at all. Because an object that's at rest, you have, John, you have as much inertia right now sitting in that desk as you have if you're running at 10 meters per second. Which is pretty fast, by the way. You have as much inertia sitting in that desk as you do if you're running at 10 meters per second. You don't want to change your motion now any more than you want to change your motion when you're moving at 10 meters per second. So what's it dependent upon if it's not dependent upon your speed? No. Mass. What resists a change in motion more than John does? A car does. What resists a change in motion more than a car? A train does. Okay, the heavier it is, the harder it is to start it moving, but once it's moving, the harder it is to stop it or even speed it up even more. A few years ago, we have two kids right now. My wife and I have two kids. When we had one kid, he was, I forget how old he was, maybe 5 years old. This probably would have been 5 or 6 years ago. I remember my wife and I went out somewhere. We had a babysitter. At that time, the Royal Bank is where our school board office is right now. You guys know where that is? Downtown? I had to stop at the Royal Bank to get some money to go pay the babysitter. So I stopped at the Royal Bank, which is, say, right here. Okay? There's the road. Okay? There's the four-way stop there. I stop right here. Okay? I run across the street. I get my money. I come back out. Okay? Then I'm going to go, here's a train tracks right here. Okay, and then there's this, you guys know there's this alleyway down this way, right? Right beside the train tracks. You guys know what I'm talking about? So I pull up here, I drive up here. Oops, the lights are on. There's a train coming. I look down the tracks. The train's coming down the tracks. So what do? I stop, right? Like any sensible person does. Then I decide, you know what? I got to change some of my money. It's all 20s, and I forget what I owe the babysitter, like $50, let's say. I need to change one of the 20s into a couple 10s. So I decide I'm going to cut around here, since the train's coming down here anyways. I'm going to cut back here to the hi-ho over here, exchange some money, and then I'll go home. So that's what I do. Okay, I'm pulling down here. The train's coming up here. Train's coming down the tracks. Okay, I'm going right beside the tracks the other way. Get my money here, exchange my money at least. Come back out here, drive back here. I figure the train's got to be gone by now, right? The train stopped on the tracks. So now I got to stop. So then what do? I decide, well, I'll cut down here. I'll avoid the train completely because I live up here somewhere, right? So I'm I go down here, I'm going to avoid the train completely. And then I realize, wait a second, it stopped because there's a van that's been T-boned by the train that's in the middle of the tracks 300 meters away from the crossing. The van that was behind me when I stopped for the crossing and I turned right to go down beside the tracks, he decided that he was just going to try to beat it. No, he didn't. He didn't beat it. He got T-boned by the train as he tried to cross the tracks. The train took 300 meters to stop. Why? It's got such a big mass, right? Inertia is a tendency of an object to keep doing what it's doing, the tendency to resist a change in motion. It was moving, I don't know, 50 kilometers an hour, let's say. What did it want to do? Keep going at 50 kilometers per hour. And because it has such a high mass, it didn't want to stop. It didn't want to change its speed at all. Yeah. What's moment of inertia? That's a different thing that we, yeah, let's come back to that maybe some other time when we're not on this thing, okay? It's not completely unrelated, but it's not the same thing here. Now, I didn't stick around there was lots of people around here helping the guy that was inside this van or whatever. I didn't stick around. But this train, when it was time to get going again, would have taken a little while to get going again. Why? Because it had just as much inertia when it was sitting there on the track as it did when it was moving at 50 kilometers per hour. It was difficult to stop that train, right? But it's also difficult to start it because it doesn't want to change its motion. Whatever it's doing, it wants to keep doing that. It doesn't want to change its motion. Static equilibrium, another term. This means an object at rest. When an object at rest has balanced forces acting on it. Static means not moving. So static equilibrium, balanced forces. Hey, John, I'm going to push on Spencer's desk. Can you push on Spencer's desk the other way, please? Okay. Just a little bit here. Yeah, please. So I'm pushing on Spencer's desk to the left side of the room. John's pushing on it to the right side of the room. Spencer's desk isn't moving right now, right? It's at rest because it wants to stay at rest. What do we know about the two forces, the one that I applied and the one that John applied there? What do we know about those two forces? They're opposite. They're equal and opposite. They're balanced. Okay, Spencer's desk is in static equilibrium because it has balanced forces acting on it. Just because something's at rest doesn't mean it doesn't have any forces. It means the forces that are acting on it have to balance each other. That's in static equilibrium. Hey, if John pushed harder, okay, John, push again. Push a little bit harder this time, though. If John pushes harder, what happens? If we have an unbalanced force, what happens? That's when it starts moving, right? That's when it changes its velocity. Okay, when we have an unbalanced force. Translational equilibrium means almost the same thing, but this is referring to when we have an object that's moving. When a moving object has balanced forces acting on it. This is the one that gives people a little bit of trouble. A curling rock is sliding down the ice. It's got balanced forces acting. A car traveling down the road at 110 kilometers per hour has balanced forces acting. It doesn't mean there's no forces. It's balanced forces. What happens to an object that's moving down the road or down the curling rink or whatever if the forces are balanced? Let it stop. It maintains its speed, yeah. It maintains its velocity. It doesn't change direction. It doesn't change speed. It doesn't speed up. It doesn't slow down. Okay. If you apply a force on something and it's bigger than the other force, if Spencer's desk was moving and John applied a force and I applied a force and the same values, then Spencer's desk would keep moving at the same speed as it was moving at. But if John's force was bigger or my force was bigger, it might cause Spencer's desk to speed up or slow down. So translational equilibrium, when it's moving, but there's balanced forces acting on it, it's going to keep moving at a constant speed. Newton's first law. Okay, this relates a lot to the demonstration we just did. Newton's first law, probably heard this before. An object in motion, what does it want to do? We kind of already talked about this already, right? An object in motion wants to. Yeah, inertia is a tendency to resist a change in motion. So if it's moving, what does it want to do? It resists a change in motion. If it's moving, it wants to stay in motion. So it stays in motion. In a straight line. And a constant speed. So it doesn't change direction. It doesn't speed up. It doesn't slow down until acted upon by an unbalanced force. A car traveling down the road doesn't want to speed up, or it doesn't want to slow down. It only speeds up when you apply an unbalanced force. Put your foot on the accelerator. It only slows down when there's an unbalanced force. Put your foot on the brake. Or wind resistance can slow it down as well. Friction can slow it down as well. It wants to stay in motion in a straight line at a constant speed until acted upon by an unbalanced force. Okay, when I was your age, I had when I was 16, I had a job. Okay, it was on Fridays and Saturdays, and it was I drove a delivery van, and I did these on Friday. I would do about a 3-hour run of deliveries, and then on Saturday would be an 8 or 9-hour run of deliveries. And I remember one Friday night it had snowed, kind of like this morning, except a little bit more snow. It was icy, no more icy than it was this morning, but a little bit more snow. And I remember driving on the highway, and then there's an off ramp that I've got to go over, got to go down, and then underneath the highway here into this town. Okay, and I remember 16 years old, just learned to drive, didn't get my driver's license until I was 16, so I'd only had them for a few months. Coming down the highway, okay, a little bit slower than the speed limit because there's snow on the road. I turn into here, what happens? I hit a patch of ice. What happens? I keep going in a straight line. An object in motion continues to move in a straight line at a constant speed until there was no friction. There was no unbalanced force acting on me. So I went in a straight line at a constant speed until an unbalanced force acted on me. What was the unbalanced force? The guardrail over here. So I went in a straight line, a perfect straight line, until the guardrail stopped me. Okay? An object in motion stays in motion, not only at the same speed, but also in a straight line until acted upon by an unbalanced force. Now, there's another aspect to it as well. An object at rest stays at rest until acted upon by an unbalanced force. This probably would have been about 15 years ago now. I was actually driving to Edmonton. I was on my way to Edmonton, but I just barely got to Calgary. Okay, I hit the first set of stoplights on McLeod Trail in Calgary. The first set of stoplights at the time, which is at Shaughnessy, right, where the Safeway is, and you turn in to go to the movie theater and so on. I'm sitting there at the stoplight. I stopped because it was red. The lady behind me pulls up behind me. She stops because there's a red light and I'm in front of her. The light's still red, and all of a sudden, for whatever reason, she just decided to go. She was stopped. She stopped for the red light. Then she put her foot on the accelerator and just drove into me. She stopped first, and then she drove into me. Anyways, she was going pretty slow, so it didn't hurt me and didn't even damage the car. Has anybody ever been hit in a rear-end collision like that, except harder than that? Yes? You get whiplash? I didn't get whiplash. Oh, was that right? So pretty hard. Yeah. I didn't get whiplash because she wasn't moving fast enough, right? But I felt it. I definitely felt it. Okay, when you get whiplash, okay, whiplash often happens in that situation where somebody hits you from behind. The reason is because your head doesn't want to go anywhere. Your head wants to stay at rest. Okay, you're sitting there at the stoplight. Somebody hits you from behind. What happens? Well, your body's at rest. It wants to stay at rest until an unbalanced force acts on it. What force acts on your body? Well, ultimately, it's the car that hits you, but directly, it's the seat back, right? The seat back pushes you forward. Agree? So your body goes forward. My body goes forward. What happens to my head? My head stays where it was. People have this impression that my head, in the event of a rear-end collision, gets jammed back like this. Does it? You're in a rear-end collision, your head goes back like this. Does it go back? Not at all. Your head stays where it is. Your body goes forward, which makes it look like your head goes back. Your head wants to remain at rest. It does remain at rest until an unbalanced force acts on it, which eventually is your neck muscles. And that's the whiplash, the neck muscles stretching. That make sense? An object in motion wants to stay in motion, constant speed, straight line, until acted upon by an unbalanced force. An object at rest wants to stay at rest forever and ever and ever until acted upon by that unbalanced force. Okay? We've got 5 questions for you to work on here, guys. And the good news is it's 3 o'clock. And we're done our stuff. So you should be able to easily finish these 5 questions before the end of class, right? Easily. And have no homework for tonight. Questions 1 to 4 and question number 6 on page 142. Okay? Let's see what you can get done on those in the next 20 minutes. If you don't finish them up, then please finish them up for homework tonight, okay?